In this screencast, we're going to talk about some of the properties of liquids. The first property we're going to talk about is vapor pressure, and this is the pressure exerted by molecules of a substance in the gas phase equilibrium in equilibrium with its liquid phase. Right? So vapor pressure, if you have a liquid, what's going to happen is some particles are going to be flung out of the liquid into the atmosphere, right? So they're going to come here to the top and they're going to be flung out here to the atmosphere. And so when we look at, right, vapor pressure, let's say this is a closed container, then you're going to have the particles here, right, above, and those particles are hitting the walls of the container, and that is what causes there to be pressure there. Now, there's a few things that can affect vapor pressure. Higher temperature is one. It means there's higher kinetic energy for the molecules in the liquid, and that means a greater number of molecules at the surface with sufficient energy to overcome the intermolecular forces of the liquid and enter the gas phase. So at higher temperature, you get greater kinetic energy. You get more molecules in the gas phase. And that means more molecules in the gas phase. That means more molecules hitting the sides of the container. That means the pressure increases. Surface area also affects vapor pressure. The greater the surface area, the greater the number of molecules on the surface. So what we're talking about here is if we had a container like this, right, and there was our liquid, versus a container that had a lot of surface area like this, and we're looking at the particles here above the surface, right? And I can't help but finish that. So there we go. What can happen is only a given fraction of the molecules on the surface can escape, right? And so if you have more surface available for molecules to escape, more of them can escape, right, and evaporate and increase your vapor pressure. Then you have intermolecular forces. And as the intermolecular forces increases, there's more kinetic energy or a higher temperature is required to overcome those forces and evaporate from the liquid phase. So greater force requires greater kinetic energy, which we talk about as temperature, is needed for the molecule to escape the surface. So let's look at some examples here. So in these two kind of examples that I have here for you, one is water. So this is water. And this is bromine, right? When we look at this, right, the vapor pressure of water is due to the molecules leaving the liquid and going into the gas phase. Now there's an equilibrium here, right? There's particles that go up and then there's particles that come back from the gas phase and condense and go back into the liquid phase. Same thing is happening here with bromine, right? Now, bromine is going to have a higher vapor pressure than water. So bromine here has a higher vapor pressure than water. And that's because the strength of the intermolecular forces are weaker than the intermolecular forces in water. Okay, and so what this means is the intermolecular forces are so weak in the bromine here that it's very easy for a molecule in the liquid phase to go in the gas phase because there's not very strong interactions between the molecules in the liquid phase. In water, there are stronger interactions between the molecules in the liquid phase, and so it's harder for those molecules to leave to go into the gas phase. So you end up with fewer molecules in the gas phase, and that means you have a lower vapor pressure. Now, let's look at the intermolecular forces in water. Water is a polar molecule that has an oxygen attached to a hydrogen and an oxygen with lone pairs. And so it's going to have dispersion forces. It's going to have dipole-dipole interactions. And it's going to have hydrogen bonds. Right? If we come over here and look at bromine, this is a nonpolar molecule because it's two things that are the same thing together. So there's an equal pull with electronegativity. And so what that means is the only thing it's going to have is dispersion forces. And so those intermolecular forces are a lot weaker. So it's going to have a higher vapor pressure. Another property of liquid that we can talk about is surface tension. Surface tension is just the intermolecular forces holding molecules together kind of at the surface, right? And so if we look here, this is a needle and it's floating on the water because the force of gravity acting on the needle is less than the attractive forces of the hydrogen bonding between the water molecules on the surface. And so as a result, the needle can't separate the water molecules and sink below the surface. Right? So these intermolecular forces are so strong that gravity is not pushing through them. Similarly, if you look here, this is a water strider. These are bugs that can walk on water. And it's because water has these strong intermolecular forces that give it this layer of surface tension. Right? Gasoline, though, is mostly made of hydrocarbons. So it only has dispersion forces. So it's going to have less surface tension. So more intermolecular forces means more surface tension. So greater intermolecular forces means more surface tension. So it has less surface tension. So the water bug and the needle would sink. Okay. Now, another property of liquids that we see is cohesive and adhesive forces. When we talk about cohesive or adhesive forces, we need to talk about the meniscus. So the meniscus is just the curvature of liquid due to these adhesive or cohesive forces. So for example, this is water with red food coloring. You can see that we have a concave meniscus. This is mercury. You can see that we have a convex meniscus. Adhesive forces, right, are the forces between the glass and the water molecules. And you can see those kind of here, right? And then cohesive, when we talk about those being adhesive forces, you can also have cohesive forces, and that pushes away the molecules, like you see here in mercury. So when you have a, right, concave meniscus, right, the adhesive forces are greater than the cohesive forces, right? So for example, water on glass. And then if it's convex, the cohesive forces are greater than the adhesive forces. An example there is that mercury on glass. Now, this results when the intermolecular forces between the two substances are similar or different. So, for example, here, right, we have hydrogen bonds between the hydrogen atoms of water and the oxygen atoms in silica dioxide of glass, right? And so those bonds make the water adhere to the edge of that glass, which is what makes it that U shape. Mercury atoms have no attractions like that, and so it forms this convex meniscus because the mercury atoms don't have those intermolecular forces to the sides of the glass. Adhesive forces can also explain capillary action. So this is the tendency of a liquid to rise in a narrow tube. Right? So if you've ever had your finger pricked and you've seen the blood rise through that narrow tube, that's capillary action. The liquid column, when we look at this, reaches a maximum height when the downward force of gravity acting on the column of liquid counteracts the upward draw of adhesive forces. So the reason that liquid or like blood is drawn up a small tube is because there's intermolecular forces between the glass and the water molecules in the blood. Same thing if we look water being drawn up a flower stem, and so we can see those both places. If it broke up there for a second, you haven't missed anything. The doorbell rang and I went back and restarted. All right, so let's talk about viscosity. Viscosity is just resistance to flow. And what we're going to see is, right, as the intermolecular forces or the strength of the intermolecular forces increase, viscosity also increases, right? And so in nonpolar compounds, viscosity increases as size or molar mass increases, and dispersion forces increase. Okay, so molar mass increases, viscosity increases because those dispersion forces increase. Size increases, viscosity increases because those intermolecular forces increase. So, for example, if you have motor oil here, it is much more viscous than gasoline because it has a higher molecular weight and long chains of molecules, which provide greater surface area for those interactions between chains. So it has a greater intermolecular force. You see the same thing in polar molecules. Viscosity increases as the strength of those polar interactions increase. Now, viscosity also decreases with temperature. So viscosity decreases as temperature increases. If you think about the viscosity of cold maple syrup, so you've got maple syrup and it's been in your refrigerator and you pour it compared to warm maple syrup, warm maple syrup is going to flow a lot faster. This is because the molecules are moving and have a greater kinetic energy. All right, so this finishes up some of our properties of liquids. If you have any questions, please feel free to pop by my office.